Advanced motor control techniques, such as vector control, are increasingly used to build energy-efficient systems. However, there are two major challenges faced by the developers. The first challenge is the solution cost. The 16-bit microcontrollers are cost-effective, but quickly run out of performance when implementing computationally intensive sensorless vector control. The second challenge is ease of implementation. Most evaluation kits in the market fall short of enabling users to tune the vector control algorithm for their own motors. Some kits enable customization using trapezoidal control, but not the sensorless vector control. Today, I'm introducing a new motor control kit that uses Renesas cost-effective 16-bit RL78 microcontroller and provides easy tuning of current and speed loops for sensorless vector control. This kit comes preloaded with code to demonstrate the motor spinning in both directions. However, if you want to perform a detailed evaluation, a graphical user interface is also provided. An application note is also included to explain the implementation of the algorithm. The 32 MHz RL78G14 microcontroller contains hardware blocks that accelerate the DSP instructions, and hence it increases the computation power of the device. In addition to that, unique peripherals such as event link controller reduce the CPU usage. Let me show you an example. In this example, the PWM rate is 24 kHz, but the control loop is running at 4 kHz. Rather than interrupting the CPU at every counter underflow, the ELC triggers another timer. The CPU is only interrupted at 4 kHz rate when we really need to update the control parameters. Features like these enable RL78G14 to drive a 3-phase brushless DC motor using sensorless vector control at up to 8 kHz control loop rate. The kit comes with a small brushless DC motor and uses the USB power supply. You may also connect up to 48-volt supply and, if needed, your own high voltage inverter through a connector provided on the board. If you want to do additional signal conditioning, the patchwork area that's provided on the board is very helpful. Now let's have a quick look at the test mode that is used to tune the current and the speed loop parameters. Shown here is the graphical user interface that you can use to evaluate the motor kit more extensively. This is the speed control window. The top half of this window shows the speed plots, the voltage plots, and the current plots. This is the speed dial that could be used to turn the motor in either direction. Now to go to the test mode, we will go to the parameter setting. The parameter setting tab lets you use your own parameters and run your own motor. There are different parameters that you can set using this tab. To run the motor in test mode, there's a magic number 22. So we will write this magic number 22 in the default parameter setting tab and just say write. Now it's written to the device, but we need to reset. And to reset, we will push on this reset button that's on the board. And let me push that reset button. Now the device and the board, they are operating in the test mode. Now if you want to use your own motor, there are different parameters that you might want to fill up. And one of them is the polar couples. So currently I have filled it up for the motor that we have. Again, this motor that I'm running right now does not come with the kit. It's a different motor, but we want to show that it's easy to tune your own motor using this test mode. The startup current is the current that you want as a startup, and then there's a maximum current. The stator resistance and inductance of the motor are filled in. The current loop Kp and Ki are the constants that we want to tune today. Now the theory behind tuning the control loop is very simple. You excite the control loop with a step input and you look for the output, and you want to make sure that it's snappy. It's not overdamped or underdamped. So we will start with a value of 1 and 1. I'm using picoscope, which is displayed on this screen right here. But if you want, you can use any oscilloscope available in the lab. So I will arm the picoscope here with a trigger, and I will send the trigger by putting 1 in the PI tuning trigger tab. So I put 1 here and I say write. The moment I say write, I go to the picoscope and it shows me how the current loop is responding. Ideally, we want to see here 400 millivolts. That should be the ideal response. But you can see that it's very damped and it's taking a long time to recover. So now we can go back and tune these parameters. Let's first tune the proportional gain constant, which is the Kp. I change it to 10 and write it back again to the device. Once I have written it, I want to load my scope again for a single capture and then again do the PI tuning trigger. Once I do the PI tuning trigger, the moment I write it, the scope will capture it. Now you can see it's becoming better. Let's change it one more time. As the same procedure, I change these parameters, I write it to the device, then I go back, arm the scope, and then trigger the PI tuning. The moment I trigger it, the scope captures it. Now you can clearly see that we have improved on the response, but there is a huge steady state error. And this steady state error is coming because we do not have the other parameter set, which is the Ki or the integral gain constant. Now let me start changing the Ki, which is the integral gain constant, and that determines the steady state error. So I change it to 100 and I write it down. I go back to the picoscope and I arm it. And coming back here again, I will just trigger the PI tuning. The moment I write it, I can see the capture. And now as you can see, the steady state error is eliminated. But still there is a certain lag. If you want to zoom in, there is a certain lag. And we can make it better by changing the parameters even more. So let me go back and change it one last time. And I will make it 200. I write the parameters down to the device. I go back and I will arm the scope. And finally, I will trigger the PI tuning. The moment I write it, the scope captures it. And as you can see, it's becoming better and better. So now we have perfectly tuned our control loop by changing the parameters Kp and Ki for the control loop. Now to tune the speed loop, it's pretty much the same concept. You want to tune Kp and Ki, which are denoted here, but to give a step response, you need to put the motor on a dynamometer and give a step change in the load torque and pretty much follow the same procedure. Look for the speed output in this tab and see whether it's perfectly tuned or not. So today we demonstrated in this demo the test mode that is used for tuning the control loop parameters Kp and Ki. And it's very straightforward and simple to tune those parameters for any motor that you may have. So as we saw today, there is no need to spend hours tuning the control parameters anymore. The RL78 motor kit simplifies this process and allows you to run your own motor using sensorless vector control. For more information on this kit, please visit our website.